So now it's time to talk about convolution, and the first thing we're going to talk about is what is meant by a kernel. The kernel defines the weights for the pixel around the currently processed pixel. This means that for every pixel that we are processing, we can take every neighbor, multiply the neighbor's value with the weight, and then add it to this center pixel. A kernel doesn't have to be 3 by 3, that is just the most common one to talk about. It can also be 5 by 5, it can also be diagonally shaped, it can also just be 2 by 2, or it can be cross-shaped, which we're going to see later on. To make it easy to try out different kernels in this example, I have exposed the 3 rows for the kernel out here on the right side, under the details panel for the blueprint. So here you can see, if we start adding values in, the picture gets very bright. And the reason it gets bright is because obviously if we take the full color of one pixel, add it to the full color of another pixel, add it to the full color of another pixel, and repeat this 9 times, we're going to have roughly 9 times as much brightness for the one pixel that we are writing to. To make it a bit easier to play with these values, there is a normalize. The normalize will just sum up all the weights and divide the final result with that weight. So now you see we get back to the same brightness that we had before, and it's just kind of blurry. But it makes sense that it's kind of blurry because every pixel takes a little bit of value from everywhere else. This gets a lot more apparent if we use a simpler texture to look at. So let's just reset the kernel. We're going to keep 1 in the middle because we want the value of the pixel that comes in to also be the value that goes out. But we don't want any neighbor to contribute. So let's grab this single pixel texture, pop it in, and now we can see, so this one is 16 by 16 pixels, so it's very easy to see what's going on. So now let's go back to the kernel and let's put a 1 in the first row in the first field, and you'll see something pops up here. You also see that it got dark, It got dark because it's now saying, well, in the kernel there's 1 plus 0 plus 0 plus 0 plus 1, so it's 2, so it's always dividing by 2. So we'll just go ahead and turn off normalize kernel. So now you're potentially wondering, why is it the bottom right pixel that turned on when we put a value in the top left? Well, remember, these are the values as seen from the pixel. So when we put a 1 up here, it doesn't mean that this pixel here suddenly is going to write to this pixel up here. We cannot write to some other pixel than we're currently processing. What happens is that when this pixel down here, that used to be black, starts looking around its 8 neighbors, it finds that, oh, there is a white pixel in the upper left corner, and so I'm gonna be white, because that's the weight that I've been given. In the same way, this one up here can have the exact same effect if we say, well, if the bottom right pixel is white, well, then I should also become white, or if it was green, I should become green. We can continue this and get many interesting results. I mean, we can do it diagonally. We can also try to put in some actual weights in here, see what happens, and if we can maybe even get something that akin to a blur function of some sort. Like that, for example. Or maybe we can even do it less here in the corners. Well, you get the idea. We might even be able to have a bit more of a sharpening effect if we subtract the middle value. So with these values, if we pop back the large pattern, you'll see it's almost like an edge detect. And that's just one of the kernels that you can choose. If we have a look on Wikipedia, we can see there is a few examples in here that you can choose. The identity is just the one that I set before using the single pixel example, where it's just a 1 in the middle and the rest are 0. We also have several edge detection options. For example, the one with minus, 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 minus and a 4 in the middle, or minus all the way around. We can try that out. Let's say well, that clearly is an edge detection. We can also do the sharpen. Small mistake. There. And that's definitely a sharpen. Then there is the box blur, which is just same value in all of them and then divide it out. So in this case, you would just go 1, 1, 1, 1, 1, 1, 1, 1, 1, and then normalize it. And then the last one is, of course, the Gaussian blur on a 3x3, which is 1, 2, 1, 2, 4, 2, 1, 2, 1. 1, 2, 1, 2, 4, 2, 1, 2, 1. And as you can see, that's a slightly more interesting blur, or at least a slightly smoother blur. But we'll get back to the Gaussian blur later on. So yeah, let's have a quick look at the materials used. If we open up the convolution material, there's not an awful lot going on. But that's because it's hiding inside this material function. I really only just have a switch out here, and then I have a divide here for the kernel sum, and then I'm just using a lerp here so that by changing normalize between 0 and 1, I can make it not divide, or I can divide it by the sum so that you're able to adjust. That was the one I turned on and off with the normalize kernel. The benefit of the 3x3 kernel is that I'm able to just pipe in 3 vectors, and when you look in the interface over in the details panel, they show up nicely in a grid pattern like this. Alright, so let's have a look inside the convolute kernel. It might be a bit much, but luckily if you know HLSL, you can compact it down to relatively little code. That is just a few loops. And if you write it in this format, it's also much easier to make it larger or smaller, or change whether or not it actually sums up all the values or takes the maximum or the absolute or something similar to that. So what's actually going on inside here? If we zoom in, we can see there's a texture object coming in, and there's a UV coordinate, and then there is a spacing option that we'll get back to later. Using the texture object, we get the dimension of the texture, and by dividing that with the spacing, which defaults to 1, we once again get our pixel size. We can then take an offset for every pixel, left, right, up, down, and diagonally, multiply it with a pixel size, which is what is happening in this row, and add it to the UV coordinate. We then sample 9 times, so that we have one sample for each kernel, and then for every kernel we multiply it with the kernel value that we got in here. This lump here only serves the purpose of summing up all the weights of all the kernels, so that we're able to output a kernel sum we can divide with for automatically normalization. So that's basically the essence of the 3x3 convolution kernel, and how to do a basic blur, sharpen, or edge detection.